Alright, so now I'm going to talk about anechoic chambers. So here's a picture of an anechoic chamber. And first we should ask, what is actually an anechoic chamber? And so basically it's all in the title. You see the word anechoic and it sounds kind of strange, but if you actually take it and break it apart, it's just, and I guess this is like a grammar lesson, but you can stick an in front of words to make them mean none. And then echoic is just simply echo, producing some kind of strange, it doesn't come from some kind of strange language, it's just simply English. So yeah, basically an anechoic chamber is just a room in which you can simulate a vast area where you don't have walls that echo anything back. And in acoustics they call this a free field acoustic space. And as I'll show probably in a slide or two, you basically have no reflection of acoustic waves off the walls, and you'll have usually almost full transmission. And of course the things they're not perfectly ideal, but if you take a lot of engineering you learn that that's the case usually. And but they're pretty close, so we can just do simulations that require an echoless space. And so the way they work is basically all the walls and sometimes the floor and ceiling as well are covered in these absorbers, and sometimes they'll be cone-shaped or stick-shaped or pyramid-shaped, as you see on here. And so basically you have all these absorbers covering the chamber, and not only are they made to absorb the sonic waves fully, but they're also, the shape of them is made in such a way that they also fully reflect away from the source. And so, as you see at the bottom of the slide, there's these equations for the reflection coefficient and the transmission coefficient. And what these say are, if you output some kind of wave, like an electromagnetic wave or a sound wave, then this coefficient will tell you what percent of that you'll get back, or what percent of that is transmitted. In the case of these cones, if I draw one like this, and let's say we have like a wave coming this way. So what's going to happen is, more often than not, the wave is going to hit some point that's slanted on these absorbers. And so what's going to happen is it's going to reflect away from the source, if the source is right here, and create no echoes basically. And so that's the reflection part. And part of why the cone shape is like this, like I was explaining, is so you can have a maximum slanted area like this, so that you're more likely to have the reflection. Because I guess to actually have some kind of echo, you're going to have to hit it like right on the tip of the cone to have like a straight reflection, like going straight back to the source, and it's very unlikely if you have this kind of shape. And so that's so the other part of it is they'll make them out of instead of making these cones out of like something stiff like concrete, or I don't know, something that would absorb some. Anyways, they make it out of something that has a good absorption rate or transmission coefficient. So although they are shaped so that they reflect, they also have a large transmission coefficient, which means that with an incoming wave, most of the wave's energy is actually going to go into the cone and be absorbed instead of being reflected. And so, although you will get some reflection, it's very small. And yeah, and that's the reason why they'll have foam absorbers. And another point is that there's different kinds of anechoic chambers too. They'll have ones for acoustic anechoic chambers and ones for RF frequency. So the difference is that in acoustic applications, like sound waves are usually, their wavelengths are pretty long and the frequency is pretty low. The length of the wavelength, the longer wavelength you have, the longer these cones need to be. So for an acoustic chamber, you'll see these cones being like maybe 3-4 feet long. But then in an RF chamber, like radio frequency, high frequency kind of stuff, usually instead of being like 20 hertz to 20 kilohertz like we can hear, you'll have like very, very high frequencies and I don't know, what's the RF range? With like megahertz, I guess? Megahertz, gigahertz? Yeah, higher terahertz even. So you have really high frequencies, and that means that the wavelength is much smaller, and as such, the cones need to be much smaller themselves. And we have an EM lab here where they actually have an anechoic chamber for RF tests, and I think the cones are only like a couple inches long. So yeah. And here's an example of, there's a couple different setups for anechoic chambers. This is a fully anechoic chamber where you have the floor, walls, and ceiling all covered in these cones, and you can see at the bottom there's like this wire mesh that allows sound waves to pass through. Yeah.
Why do they alternate horizontal and vertical?
Probably to help with the reflection, I'm guessing. My guess is that they're trying to maximize the reflection away from the source, and so if you do that with kind of haphazard patterns, it's maximize that. I hope maybe
The diffusion.
yeah. Yeah. Okay.
Because if they're all in the same way, then it all gets reflected the same way, and it'll make the reflection stronger.
Mm-hmm.
Well,
Okay.
well, each of those individual ones will have, like strengths in certain frequencies, and if you offset them, you can get rid of some of that. Basically.
Cool. Yeah. So you see they have that wire mesh on the floor that lets the acoustic waves pass through without bouncing off, like in the case like a floor like this. Yeah. Go.
Is there any rule to like how big the meshes are supposed to be? Because it seems like if you still like, I don't know if it's good to record that thing, but for example, if you do want to set up a studio there and you don't want to reverb or anything like that, you would do that, but then you need a place to put all.
Yeah, exactly. Yeah, which is why they'll use the next case, a semi-anechoic chamber, which it's less ideal, but it's also more practical. Like you see, you can actually use a car in there, and yeah, the difference between the two rooms is their uses. Obviously, like you can't have a lot of heavy use in a floor or in a room like this with that kind of floor.
What would this be used?
Simple tests like that where you have, like you're saying, you can't really have like a bunch of heavy stuff in there. So like in that case, it looks like they're just testing out one speaker, and then they have like, they just have like a speaker here, and then some kind of maybe a sound emitter or even a mic. So yeah. And then they'll have semi-anechoic chambers, which is less ideal but more practical. Yeah, and so these anechoic chambers are used for a whole bunch of stuff. I thought this picture is pretty sweet. All the anechoic cones on there are just like little rods basically, and they serve the same function, but they look crazy. And so people use this, like Kelton was suggesting, for recording music. And say you want like a really clean sound to your music, you would want like no echoes, because usually you can use echoes for like more natural sound. Yeah.
Yeah, I do have a question for you. Because like a lot of people like add reverb, like even if like you talk about a lot of people like to add reverb to make the sound more.
Yeah.
So what kind of things can you record in a semi-anechoic chamber?
In a semi-anechoic.
Yeah.
Actually, they'll use stuff like here, like part of the reason why we use anechoic chambers is for noise tests, like with cars. And so you know how on some commercials they'll demonstrate how inside the car you can't hear like anything from outside. And so I guess that's part of it. They'll just do sound tests like that, or actually.
What about like studio application?
Studio application of a semi-anechoic chamber.
Yeah.
Just like you're saying, where you have like all this heavy stuff, and you need a floor to put it on.
Well, I mean, like, would it really benefit your sound? I guess.
Yeah, but if you did it with an anechoic chamber, then you would be able to add in the reverb and post it instead of having this natural reverb. So you could actually control the reverb instead of not being able to control it. Yeah, like
in a studio, would it be more applicable to use an anechoic chamber facing, like the room that you're monitoring the sound, you can like adjust your frequencies, like, and have the people actually recording in a different room. Wouldn't that be what you would use it for?
Yeah, things, when you record music, it's actually usually good to have some reflection, because without any, it does make it sound really flat, actually.
Yeah.
Like, when you do vocals especially, it's usually good to like be inside one of the semi-Anechoic chambers, but put like a piece of wood or something behind you.
Yeah.
Because a lot of the reflection that comes from behind you helps to deepen the sound.
Yeah, that would make sense. Just like, yeah, right.
So these things that you have in this picture, those are diffusers, right? So they don't absorb much at all.
Yeah.
What they're doing is destroying standing waves, and so basically, yeah, like absorbive anechoic chambers. What they do is they only really take care of the higher frequencies.
Okay.
And so you end up with a bunch of low, and that's where you get that dull, flat sound, is that you have this low frequency overpowering everything. And you use, the diffusers will give you the much more natural, like sounding like there's, like you're in an open space, as opposed to being absorbed.
All right, and yeah. So, as I was saying, some uses for anechoic chambers, they'll have them for recording music, and also have them for product testing and research. And some examples on here for hearing aids, vehicle noise levels, like I was saying, like for instance, they'll have like a car in a room, and they'll just be rubbing it, like say even like an electric car. We just helped a group of mechanical engineers last semester whose project was to add an artificial sound to electric cars because they're too quiet. And so the reason why they probably found out they were too quiet was A, because they were test driving them and people couldn't hear them as they were walking around, and people were driving past them in these cars. And B, they probably did these noise level tests in an anechoic chamber and probably used like a dB meter and found like, yeah, that's actually pretty hard to notice. So, and also use anechoic chambers for appliances like washing machines and stuff to get some actual numerical data to find out, yeah, is this like actually really too noisy, or would people be able to stand this? And they'll also use anechoic chambers for getting transfer functions of speakers. And basically the transfer function is, it shows you the speaker's frequency response, basically, or it is the speaker's frequency response. So if you have frequency, if you're varying the frequency, then we take a look at how much that frequency range is amplified. Then you get like something like this for the speaker. And so basically, at this frequency and this frequency, the speaker has like a lot of response. So it's going to accentuate sounds at those frequencies. And then there'll be like some flat response over here. But they'll use anechoic chambers to basically grab data from the speakers and present it cleanly like that without having interference from echoes. And like I said too, with the RF anechoic chambers, they'll have RF tests too, for like antennas and stuff. Anybody got any questions? Cool. Here's my sources. And that is anechoic chambers.
Yeah, is that a picture of the 405 one?
Huh?
Is that a picture of the 405 one?
No, I couldn't get a picture of that.
Another.
I'd be close enough. Cool. Anybody else got any questions?
Yeah, state noise. GE Lighting, where I worked this summer, had a very poorly calibrated anechoic chamber for just testing EMI radiation on their DC-DC converters. Another use.
Yeah. Cool. Bill?
I guess I also used the RF chambers. We actually had both where I worked. We had a small microphone anechoic chamber for testing microphones for our cars. So the frequency range for car microphones may only go to like 200 or 300 hertz. So the wedges are much smaller. So you get, and the chamber volume is much smaller. So like the one in Comarts, I think might go down to 20 or 30 hertz. and this one was like 150, 200 hertz.
Yeah.
So, and then the RF one, they use, the wedges are usually doped with a ferrite absorber to do RF absorption. Otherwise, it's the same idea. And then and the depth of the wedges has a relationship to the low and frequency response.
Is it quarter wavelength? I'm trying to remember.
I can look it up. But yeah, you do a lot of like product testing, like we said, you know, is my switch mode supply or is my microprocessor bus too loud? Or
One thing I forgot to mention too is that because the cones are pretty long for acoustic chambers, that means that the actual size of the room is big on the outside, but then the inside is going to be much smaller due to that, especially for a fully anechoic chamber with the floor covered and everything. So you have this huge room with very small amount of space on the inside, and the cones themselves actually cost a lot of money to make anyway, so these really rack up a lot just for a tiny space.
Yeah, they have to be custom, don't they, if you have a fully anechoic, because your door and you have to like.
Yeah, that's
walk
the other
in
thing
and
too.
everything.
Yeah. Yeah, there's all sorts of weird things with them.
The RF cones, they're $100 for a 2-foot by 2-foot panel.
Yeah, that's
Yeah.
insane. Yeah, right.
The size of the cones like make a big difference.
Yeah, they determine what frequency range you can work with. Yeah.
Can you really speak with the small ones?
I suppose so. I haven't thought about that. I've never seen it really used up.
What was the question?
He was asking if you could interlace small and large cones to cover different frequency ranges.
Yeah.
That would make sense. Okay.
There's fancy tricks of using different surfaces on the end, like the fact that one was you know, the one with the tiny squares, a whole bunch. You know, you can have the ends be at an angle, or you know, you wouldn't do curve, but oh no, the one before with the sort of random one.
Oh,
Yeah.
yeah.
So there's other options, and they'll each have different effects on that.
Yeah.
And it's very, and also like the, not just the depth, but like how thick you make them. You get all this the edge effect thing.
Yeah.
Where the wave sort of follows. It's complex, but there's a lot of ways to do it.
Yeah, if you take a lot of double E classes actually deal with wave motion, of course, EM, and also acoustics, even though that's more mechanical, but if you're a double E, that's a great class to take too, could help reinforce a lot of wave motion ideas for me. But,
Is there a cheaper way to make this? Like, it won't be really good when it's something like that.
yeah.
You can put up a semi-anechoic chamber for like $300
Yeah.
less.
There's also cheap things they'll do. I think I've seen people use like egg cartons on the walls and stuff.
Paper egg cartons.
Yeah, exactly. Or they'll just use.
Yeah, it's all just about finding the right phone.
Yeah. In the, must have been a year ago now or so, there was this house we used to jam in after AEE meetings. And instead of doing 201 homework, we would go there and just play music. But basically, we played in this little basement room, which you can imagine cinder blocks aren't really they're not very much fun to play with a full band in. So the guys there just taped up big comforters and stuff and whatever they had against the walls, and it did help too. It was surprising, but you do what you can with what you have, right?
And so there's a danger in doing that a lot though, especially if you're trying for recording, because you'll get rid of all the high frequencies, and so you'll think, oh, so everything's great, everything's gonna work fine. But you'll have really excessive low frequencies, and it'll just, it'll wreak havoc on recordings with multiple lengths at least.
What about someone said like when you're mixing or when you're recording?
This is when you're recording, and for mixing, you just won't be getting a clear, picture of what it is.
Yeah.
So when you're doing the final mix down, it's good not to do an anechoic chamber, or is it good to have an anechoic chamber and not an anechoic chamber?
Well, you want more echo for the mixing part. Or the big important thing is just to have.
Typically, rooms tend to be somewhat like listening rooms in houses. I mean, the old way we did it was you mixed for people to listen to records in their living room. So to mastering is especially still is just like a hi-fi system, and then a mixing setup may be a little bit more analytical to try to figure out
So
balance. So a little bit less echo maybe than on mastering stuff.
So, yeah, symmetry would be much more important, symmetry in the room for mixing. For recording, you actually want to avoid that.
I think this should be a four maybe.
Probably.
Yeah. Okay, so, anybody else have any questions or anything? Cool. I guess then, that's it for this week's meeting, guys.